Hello. So in this video, we'll talk about a simple test that will tell us that a series diverges. As you can tell from the name, it's a test for a divergence, right? A divergence of a series. So I'll give you a few examples here to demonstrate what I'm talking about. These two series here are divergent. N squared over n squared plus 1 and 1.02 raised to the nth power. Now, the second series here, we already know why it diverges, right? This is geometric, where your common ratio is 1.02, which is larger than 1 in absolute value. Therefore, it's divergent. One easy way to kind of understand why that diverges is just try to remember what we're adding here, right? Or what we're doing. This means let's add up all these terms: 1.02, 1.02 squared, 1.02 cubed, 1.02 to the fourth power, and so on. Right? And so the question of whether a series converges or diverges really means, does this infinite sum add up to anything finite, right? A specific number. And in this case, it's actually quite easy to see that it does not add up to a finite number, even without thinking about that whole proof about why geometric series diverges if your ratio is larger than 1. What's happening here? Well, as you keep adding terms and more terms and more terms to your infinite sum, 1.02 to the nth power, what happens to that individual term? It actually goes to infinity. Right? It goes to infinity quite slowly, right? But it's still an exponential function where the base is larger than 1. So as you keep adding more terms and more terms to your series, you're not going to approach a specific number because the terms you're adding themselves are blowing up individually. Right? So there's no way that this can converge. Similarly, for this first series here, n squared over n squared plus 1. In this case, well, I'm not even going to try to determine what the partial sums are, S sub n. But again, if you look at your individual terms, as n goes to infinity, what happens to not S sub n, right? Not your partial sums, but just your term here in your series, A sub n. Well, as n goes to infinity, the terms that you keep adding to your series, look at that limit. That limit is 1. Right? It's a rational function. You know the horizontal asymptotes are. In fact, okay, fine, let's do it this way. One way you probably remember doing in calculus. I can divide by n squared and write it this way. And now it's clear that it's 1 over 1 plus 0, which is 1. Okay. So it's not the same as the geometric series here on the right. Here, the individual terms blow up to infinity. And so clearly, you're not going to approach a finite number when you add up infinitely many of these things. But the same actually holds here. Since the terms you're adding to your series approach 1, your infinite sum, at each step that you're adding a term, it's going to grow by 1 each time. Roughly, right? Which means, again, there's no way that the series on the left converges. And in fact, what these really tell us here is kind of an opposite statement. It actually says, for a series to converge, it must, first of all, satisfy that the limit of the individual terms that you're adding, a sub n, is equal to exactly 0. Can't be infinity. It can't be 1. It can't be anything other than 0. Because if it were some non-zero number, that means when you go to infinity, again, you're going to be adding that non-zero number each time you add a new term to your infinite series. So you're not going to be approaching any specific number for the whole sum. And so this is called a test for divergence. Because as we see from the first two examples here, if you can determine that the limit of the sequence a sub n is non-zero, or maybe the limit doesn't exist, maybe it oscillates between two numbers, for instance, then the series diverges. So we can use this to very easily say that a series diverges. Right? Again, just look at the term, say, hey, it approaches 1 and that's not 0, therefore it diverges, and you're done. And that's really fun. It's a simple solution, but one that intuitively really makes sense because of this first statement here. For a series to converge, the limit must be 0. So if the limit were not 0, then the series diverges. Right? And so, well, on this slide, I have the exact same statement, just typed up here. If the series is convergent, then the limit is 0. And I'll write the other statement as well, the fact that if the limit is not 0 or does not exist, then immediately you can say the series diverges. Okay. And it bears emphasizing here, we cannot use this to conclude that a series converges. Right? And by this, I mean this test. Just look at the logical implication here. If convergent, then we know something about the limit. It's equal to 0. If we know that the limit is not 0, then it diverges. In fact, in terms of logic, these are what's called contrapositives of each other. Right? Where the first statement here is if P is true, then Q is true. And the second statement is, well, if Q is not true, then P is not true. Right? Well, you don't have to bother yourself with this too much, but for those of you who know what this means, then this is essentially what's happening here. What we can't say is that if the limit is equal to 0, then the series is convergent. And this is called the converse of your original statement. Right? This is if Q is true, then P is true. And given any implication, it's not always necessarily true that the converse also follows. Right? For some statements, it does. For this one, it doesn't. And an example of that is this one. The series 1 over n. Right? This is the series 1 over 1 plus 1 over 2 plus 1 over 3, and so on. This is actually what is called the harmonic series. Right? So you can look it up if you want on Google harmonic series, go on its wiki, read up on it. Actually try to discover why it's called the harmonic series. But this is actually an example of a series where the terms do approach zero, but the series itself, when you add everything up, it still diverges. So it turns out that it's not enough that your individual terms approach zero, right? So that's true here. As n goes to infinity, whatever it is you're adding to your sum gets smaller and smaller and smaller and approach zero. Well, whatever, it still diverges. In the sense that this infinite sum will not approach any finite number. And we'll prove this in another video. But moral of the story is, be careful. There's a reason why this is called the test for divergence. Right? You cannot use this to say that something convergent just because the limit is zero.